12, and section 12.1 is called simple harmonic motion. I need to finalize your notes on this, so they'll be on Moodle, but toward the end of the day. I'm not going to give you homework on this tonight. I'll tell you now. You'll probably have homework tomorrow night on it. Okay? So, Stasha.
Are there problems that's changing to be part of the test grade?
Let's discuss tomorrow. Can I ponder that again tonight? I want to look at the second quarter grades, which I haven't finalized yet.
Nicer grader.
Okay? I haven't finalized the second quarter grades yet, so I want to look at those and see how we're doing. Okay?
Wait, Ned grades those?
Yeah.
Ned grades most of them. I'm grading this one right now, actually, the one that you guys turned in.
Wait, Ned, that's why they're so
Yeah, he's such a mean grader.
I actually look at them after he grades them, and I don't usually disagree with any of his numbers. If you ever have a discrepancy, you can see me, but nobody has ever done that, so I haven't really gotten into much with that.
But I want to, if you argue...
You could come in and say, like, hey, Mr. Howe, I thought, this might be something I should get more points for. Let me know why it was this, and I'm happy to go over it always.
It's like you get, like, a decimal point off, minus 10 points. Oh, down to 1.
And when he does a quarter point off. That is so bad.
Well, every problem's worth 1, so he's trying to, instead of taking a full point off or something, give you a quarter off.
Wait, it's really, really so...
My grader for it's snowing a lot, yeah, but it's not sticking at all, actually. It's too warm,
Are you
apparently.
serious?
Yeah, nothing's sticking. My grader for my math class is a lot tougher than Ned is on that.
Who is that?
Why?
Hannah.
Oh, I thought you were going to say...
She grades the freshman honors algebra 2. And she's definitely a tougher grader than Ned is for that.
Have you one of your graders next year?
Yeah, you can.
So much fun.
Guys, as seniors, you're able to take an elective course where you're a TA for one of your classes. So she's the TA in the math classes.
Yeah.
Yeah.
You get to hang out and
It's like a partial credit course. They get a grade and stuff also.
Oh, really?
So yeah, next year you can request and you could say, I want to work in physics or work in math, and they'll set you up. Usually they ask the math and science teachers if they need people to help with grading, because we have the most grading. Max, can you take AP Physics next year? Okay. If you, listen carefully, the question was, can you take AP Physics next year? The only way you can take AP Physics next year is as follows. AP Physics as a senior is not only physics, but it's calculus also in it. Which means that this summer, you would have to take pre-calculus, which is possible. You can do that.
Wait, but that means...
Listen. Hold on. You have to take pre-calc this summer so that next year you're in AP Calculus. Okay? So what that means is that you need to be really doing well in math, and over the summer take pre-calc, and before you come back at the end of the summer, you take a pre-calc exam to see if you actually did enough in the summer or not. If you do well enough on that pre-calc exam, you're then placed into AP Calc, which enables you to take AP Physics. Okay? Yeah. I mean, another thing you might be able to do, I'm trying to propose a class, but I don't know if it'll happen next year, but I want to teach a senior engineering elective. So you know how there's forensics? It's like the other science. I'm going to see if I could teach an engineering course for seniors, where we do like computer one semester, 1 quarter, mechanical 1, environmental and civil 1, and then what's another sect of engineering? Chemical, another. So doing the 4 types of engineering, or 4 or 5.
Do it. Yes.
It depends. It always depends. It depends on if, I needed to teach other courses where I can't do that, and if the teacher amount adds up. There's a lot of...
That's fine. Make a petition. That's awesome.
What's that?
Like 30 kids signed it with that.
And make like a petition so that...
Well, it's not that. It's a matter of if we have enough teachers to teach additional courses, too. Like, if I have to... Like, right now I teach the 2 math and the 2 physics. If, for example, like say the 2 math courses next year became 1, and then I had 2 physics, I could teach my 4th science course or my 4th course as engineering. So I'm in work on that. I'll keep you guys posted for sure. Okay?
Made us a promise, Mr. Howell.
It's not a promise, no. It's just a hypothetical. Do you have a question? I stopped you a minute ago.
Oh, yeah. I was going to actually say that means you would move up in your math as well.
For me, you mean?
No,
Yeah.
I'm saying, yeah, you would not only, because if, let's say, I'm in normal algebra 2 this year, and if I took calculus or
Well, you don't need calculus to do the engineering. Yeah, you were just being pre-calc.
But then if you did pre-calculus, then you could next year skip pre-calculus as a senior and calculus or AP?
AP Calc, yeah.
There's no such thing as calculus.
Not here, no. There's no regular calculus because we have so many math courses as it is. We have AP Calc, we have AP Stats, and then we have discrete math. Those are the 3 senior math courses. And pre-calc, obviously. Discrete. Yeah. AP Bio? Miss Myers is the teacher, but I'm sure it's like just your previous science grades and your bio grade. There's probably requirements she has. But AP Bio is very tough. Okay? It's not like the easy AP, and especially because this year they changed the entire curriculum for AP Bio. So the test this year is completely brand new. It's different from all the old tests. So I know that that's definitely one of the tougher courses right now. Not saying that you shouldn't take it, Luis. I'm just giving you, like, so you know. Max.
What's the one where what's the kind of engineering you build bridges?
Civil. Civil is probably the easiest of the math engineerings that there are.
What about where you build cars?
The toughest is mechanical. That'd be more mechanical.
Is that hard? That's the hardest one.
It's probably the toughest when it comes to math. That and chemical have tough math in there. Computer, there's math, but it's a lot of like different kind of math, like coding and looking at binary operations, which is math, but it's not the same. There's definitely calculus involved in computer, but once you do enough with computer engineering, you don't use as much calculus as you would in mechanical.
Is AP physics like a challenging, really hard?
It's tough, but I took it. I got a 5 in the exam when I took it. It wasn't like crazy difficult. On the physics one, yeah.
Because I could take it because I'm going to AP Calc next year.
Are you?
Yeah, so I'm already in pre-calc.
So you should take it then for sure. Absolutely.
Kind of weird.
You're ahead of the honors physics class already this year. You'll be more than prepared in physics for sure. It's a matter of whether your math is prepared. And if you're already in pre-calc, then you should try to take it next year. Yeah, you'll do well. You'll both do very well if you're doing well in this class. Trust me. Yeah. And the best part about next year is in AP Physics, all you do is mechanics. You know how we're doing this whole semester on electricity and magnetism? You're not, but I'm saying, everything we did in mechanics, you're going to look deeper into next year. That's what it is, really. You're not going to be doing any electricity and magnetism. So you spend the whole year, and you do things a lot slower, but you do more calculus in it. Less mu. You'll have mu, but you'll go slower on it and stuff. Mr. Donachik is the teacher for it.
Wait, Mr. John's
AP Calculus. AP Physics.
Oh, he teaches AP physics?
I thought you did.
I teach the 2 regular physics. He teaches the honors physics for juniors and the AP Physics for seniors. He's always been doing it, so it's not one of those things,
Do you not take science next year?
I do, but it's just...
Do we not take?
Well, talk to him about what you were just saying. He asked the question, so...
Yeah, but you can do engineering.
All right. Let's start with an introduction. So, Paul, up here. All right. That's okay. We talked about springs already this year. Okay? And remember, just recall in your memory. You don't have to write this part down, but remember this formula we talked about already. Potential energy in a spring was 1/2 kx squared. Before we get into this topic, because we're going to look at springs, who can remind me, what does K mean? Max?
That's the spring constant, right?
The spring constant, what does that mean though, Max? What is the spring constant?
Depending on if it's a really if it's like a big string
Let's use strong and
strong, then it has a low constant, isn't it? A high constant.
a high constant. Very good, a high constant.
And if it's not strong, then it's a low constant.
Good. So,
What's it called again, though?
you have the spring stiffness or the spring constant, you call it. Okay? So the rigidity of the spring. If a spring, listen gentlemen, if a spring has a high K value, it's a very strong spring. If a spring has a low K value, it's a weak spring. So we talked about the example between your pen and the spring there versus a car and the springs on the suspension system. Okay? Where the K value on a car would be much higher. Now, the question you might have is, where does this K value even come from? And this is what we're going to talk about today. Okay, we're going to talk about this today. So, what I want you to think about is yourself a little image. Draw yourself like a ceiling. This is a ceiling, okay, with a spring hanging from it. With a spring hanging from it. Now, if I were to walk up to the spring, and let's say I took this Purell bottle, okay, and it was a really, really weak spring, and I somehow hooked this onto the spring, what would happen to it? It would stretch and it would oscillate, right? And it would do this. It would wobble back and forth like oscillatory motion. Now, what we want to think about is this. Here's what it would look like now. Come on. What it would look, say again?
A circle? It would be the same as the as a circle turning, right?
Yes, but slow down, not just yet. We're going to get there.
Come on, Sean.
He's right, he's absolutely right. That's a good point. And that's where it becomes a sine and a cosine wave. All right, so this is what would happen, right? You would see this deviation. The minute you attach a mass to the end of it, it's going to naturally get pulled downward. Now, I'm going to give you a hypothetical, okay? Here's your hypothetical. The length of the spring when it's at rest is 10 meters. Okay? The minute I attach this mass, let's say the mass is 50 kilograms. Okay, 50 kilograms. The minute I attach the mass of 50 kilograms, we'll say that now the length is 15 meters. Okay? Well, you know what, just to make this, because I don't want you to have a misconception, make it 16 meters. I know it's weird, but you make it 16 meters.
Wait, the weight doesn't count for the string?
That's a good point. Thank you, Max. Springs are theoretically considered to be what's called massless. Okay? So whenever we look at a spring system, we're going to assume that the spring, its mass is so little that it doesn't really account for anything. So the mass of the spring might be like, 0.2 kilograms, which is 200 grams. But look at the mass itself, 50 kilograms. It's so much bigger. So the mass of the spring is insignificant. It's negligible. We could ignore it. Okay? Now, in the next scenario, let's say we attach a mass that's double the other mass. Which is how many kilograms?
100.
Now I'm going to tell you that the length of the spring is 22 meters. So, we've got, just so it's clear, we've got a natural length of 10 meters. We attach a mass of 50 kilograms, stretching it to a distance of 16 meters. We then double the mass and notice that it stretches to 22 meters. Raising your hand, can somebody make any suggestion or notice anything about what's going on? Paul?
The mass is proportional to the length of the spring.
That has been
Doubled.
good, stretched, very good. Proportionality, very good. Proportionality. So we know that this deviation was what? How far was 16 from 10? How much did it deviate? But then we doubled the mass, it went another.
6.
So we can see that as the mass doubles, the delta x, or the change, also doubles. So as we said, they're proportional. Now, what I want you to know is this. If the mass is 50, then we can find the weight of the object also by doing mg, right? Remember, mg is the weight. So let's write this down, please. The weight of this would be 50 times 9.81. Okay, 50 times 9.81. Nine times 5 is 45. What are we going to get for this? 49 point something, right?
Yeah.
What is it? Oh.
Watch it.
I think it's approximately 49 and change, right? Somebody want to check for me?
49.605.
No, it's not 49? Oh, 490, sorry. I apologize.
I mean, it's 9 times 81 times 50.
I mean, it's just half of 981. So it's going to be 490.5.
Oh, I was so good. I was 49.
So,
190.56.
we looked at the example with mass, but what we really think about is that the force applied to a spring, is proportional, you should be writing this, the force applied to a spring is proportional The force applied to a spring is proportional to its change in length. To its change in length. Guys, stop. Come on. To its change in length. How do we write that mathematically? Here's how you write it. F is proportional to delta x. And we're going to write an equation in a minute that comes from. But that's what that means, really. Again, I know this is weird, but I want to show you the symbology so you can see it. F, the force applied to a spring. This is a symbol called alpha in the Greek alphabet, which means proportional to. Come on, guys, stop. The force applied is proportional to the change in the length of the spring. Now, the proportionality constant turns out to be K. That's where K comes from. And the equation we're going to use is this. Now, I just put X there, okay, but know that this is really delta X. But you're going to see just X in your textbook, and in all your formulas, you're going to see negative KX. Okay, but this X, the force is the force applied to the spring. K is the spring constant, and X is the change in length. Please jot that down right here. This is really delta X, but you're going to see it written as X only. Max.
Is it negative because the spring, why is it negative?
Okay, I'm going to explain that now. I'm going to give you a reason for the negative, because that's one thing that confused me in high school too. So, here's the reason why. Take a look at this example here. Imagine you have a spring with an object at the end of it, and Masha walks up to the object and she pulls on the object so that it moves to the right. We consider the right to be positive, right?
Yes.
So which way is the spring pulling?
Left.
So the force of the spring is negative in that case. So it's opposite the displacement. Okay? If this were pulled to the right, the spring would pull back to the left. Now, Max, what if you walked up to the spring and went like this? And you pushed the spring and you compressed it. Which way is the spring pushing now?
To the right.
So when you push negative, it pushes
Positive.
again, indicating that they're opposites. Okay? So the spring force, write this down, the spring force will be opposite the direction of the displacement. The spring force is opposite the direction of the displacement.
Opposite
Okay.
direction.
And it's logical. We call this, ready? Write this down, please, in quotes. This is a restoring force because it wants to restore it to its original shape. These are words you might not see in your textbook, but they're words to know. It's a restoring force. Whatever you're doing with that frequency thing, stop. Whoever that was, I don't know what that was there. So, restoring force. Okay? Now, what we want to remember is that springs always have a free length. You're going to hear the term free length, so write that down, please. The free length is the length of the spring when there's no force applied to it at all, the normal length. So when you take your spring out of your pen and it's sitting on your desk, that's the free length. So it's the natural length of the spring
Is the length of spring?
when there's no force applied to it.
Learn that.
We already talked about that, yes, with potential energy. So this should be a reminder or a...
Is there a variable for that?
Say again? No, this, all you need to know is this formula here that's in the box. Let's write down our units, please. Units of force are always what? So let's write down Newton here. Units of X are what?
Meters.
Okay, so by default, if you solve for K, you move the M over by division.
N over M.
N over M, very good. Newtons per meter. Okay, think about it. Here's how you can always find the dimensions of any unknown. If you solve for it. If you solve for K, how do you solve for K? You divide by X, right? So you get force over X, which is Newton over meter. And look at it, doesn't it match up? The meters cancel on both sides, don't they? If you were to check the dimensions for dimensional analysis, these meters would cancel, leaving behind Newton equals Newton, which is true. So the units of K, which you know already from potential energy, are newtons per meter. The units of displacement are meters. The units of the force are newtons. Questions so far on this? Questions? Okay, let's do a quick example. Right, please. A force is applied to a spring with a natural length Remember, I use the word natural length here. It could also say free length. So those are interchangeable. You might see one or the other. With a free length or natural length of 13 centimeters.
Oof, conversion right there.
Oof. If the force has a magnitude, it's all right, of 25 newtons per newtons, and the spring stretches to a length of 18 centimeters, find the spring constant.
You're funny, kid.
Good.
So we can always use that equation, Fs equals kx, negative k.
Absolutely. Find the spring constant. A force is applied to a spring with a natural length of 13 centimeters. If the force has a magnitude, remember magnitude means the numerical value, not direction, has a magnitude of 25 newtons, and the spring stretches to a length of 18 centimeters now, find the spring constant. Quickly, let's write. Givens. F is 25 newtons. What is X in this problem?
Oh,
It's 5.
Fernando.
13 minus 18.
Yeah. So what is it?
Negative 5. Negative 5.
Yeah. So it's going from 13 to 18. We can consider a positive or negative in this case. If I'm considering it that if I had a diagram like this, okay, then it would be moving to the right, so I could say that this is 5 centimeters. Okay? So
I was thinking the other way.
that's fine. And again, it doesn't matter. Now, if I did it like this, then my force would have to be what? Which way is the force pulling?
The other way.
To the left. Again, if the object is again, sorry, so this force here is 25 newtons that's pulling on it. This force is 25 newtons to the right. So what's the force of the spring?
Negative.
Yeah, so let's write that below it. I know they look like the same, but they're actually two different forces. This is the applied force here by some person pulling on it with 25 newtons. The spring pulls back with negative 25 newtons. So we have to write a negative in front of our 25 right here, please. The negative in front of the 25. Okay, that's the force of the spring. And that's really all we know. Can I use this formula the way it is? What should I do to my units, my dimensions?
0.5.
Yeah, good. 0.05 meters. Convert, please. Centi means 100. So 100 is 2 decimal spots. Move it over 2 decimal spots, or 100th rather. So we want in newtons per meter. So we have Fs equals negative Kx. So we have Fs over negative x equals k. See what I did there? I divided by x, and I also divided by that negative to get rid of it. So divide by negative x on both sides. The negative cancels, becoming a positive over here, and the x's drop off, leaving you with k equals Fs over negative x. Which makes sense now, doesn't it? Because what are you going to have? What over what? Molly? Negative over negative. So we have negative 25, which is the spring force, not the applied force. Not the applied force. Again, we use the negative 25 because it's the spring force. Somebody's computer is making that. It's all right, it's all right. It's all right, negative 0.05 meters. Okay? You're going to end up getting 500 for your value. I'll see everybody tomorrow. Have a good night. Feel free to read over section 12.1. We're going to continue from that tomorrow if you want to read 12.1 tonight. Jeff.
I have therapy on Wednesday.
Okay, so again, that was the formula from yesterday. The force felt by a spring is equal to negative kx, where x is the displacement and k is the spring constant. We call this Hooke's law. Hooke', law. Named after, I think it's Robert Hooke, if I remember correctly, his first name. Okay, just a scientist who came up with the theory. Now, one thing I want to add from yesterday as well is this. This law only holds true for small oscillations. Okay, small oscillations. So what that means, and think about it. If I take, I don't know, if you take the spring out of your pen and you just lightly pull it apart and push it together, it'll move back to its original shape, right? But if you take the spring out of your pen and you pull it really hard, what's going to happen to it?
It's not going to be a spring.
Yeah, it's not going to be a spring anymore. Now it's going to be a metal wire, right? It's going to permanently deform. So the idea of an oscillation is that you can stretch the spring by little distances or relatively small distances. Okay, so please write that down. Again, small x values. Okay, relatively small. So if the spring is say you have a spring that's 10 meters long, that's 30 feet long, a spring. So you can maybe oscillate that a solid 10 other or another, say 2 meters, another 6 feet. But if you have a spring that's only this big, and you go to stretch it, and you try and stretch it a distance of 12 inches, it's not going to work, right? It's going to permanently deform the spring. So when I say small x values, let's write the word relatively. And what that means is relative to its free length. So if the free length is 2 feet, maybe you could stretch it a half a foot. If the free length is 10 feet, then maybe you can stretch it 2 feet. So the x value, that small value, is different depending on the scenario that you have. Okay, but generally speaking, these are small oscillations. And if you go on to study engineering, you're going to talk about a small angle approximation, and that has to do with a pendulum, and it's really the same idea as this. It's only a small angle. If you deviate too far, the law does not hold true. Okay, and we're going to talk about part of that today. So, let's quickly discuss the idea of velocity, acceleration, and position with regards to a spring. And this is going to be all theoretical. So remember the problems that are like multiple choice and those short answer? That's the kind of thing we're going to do now. The thing we did yesterday, when we solved for k, that's the numerical component of it, which should be very easy. You give an f, you give an x maybe, you can find k. Or you're given the free length and the stretch length, you subtract the two to get x. So the thing we did yesterday was mathematical. Now let's take a look at something that's a little more theoretical. So what I want you to do is draw 3 pictures. Okay? So we're going to draw 1, 2, 3. Okay, just like that. 1, 2, 3. This is like the wall and the ground. So this is like the corner of the room in a sense. Imagine there's a spring attached to a mass. Okay, so I'm going to draw it, and I want you to draw it just like I am here. Okay, just like I'm drawing it. So in the middle one, we're going to write the word free.
It looks
Okay.
like what's it called?
The heart thing.
Yeah, heart thing.
Measures your heart rate.
EKG or the heart monitor. Now, the second one, please do this. Draw it so that it's further to the right. Just make sure it's further to the right.
Why would you put
I'm drawing the free in the middle for a reason, I know. Okay, so the free one is like as if the mass is at rest. The top diagram is as if the mass is like stretched, okay, all the way stretched out. The bottom one is going to be like it's compressed. Okay, so make sure you show there's a difference. This is the same spring, we're just looking at it in different terms or different times.
Is the top one when you stretch it?
Yeah, and the bottom one's like when it's being compressed. Okay? Now, the middle one, please write this word down. We call the equilibrium, God bless you, equilibrium position. Just like we talked about force equilibrium, the middle one again is called the equilibrium position.
Wait, that's last one?
The middle one.
Benji.
Whenever I call Cincinnati, it's and everyone says that. Whenever I see you,
People think of.
But I don't want you to die.
Jeff, everyone wants to bless you, that's why.
Jeff,
Bless your face.
It sounded like a sneeze though a minute ago.
yeah, it's not sneeze.
Alright,
I just talk my ladies by coughing.
now do this please next. For each of these diagrams, mark the middle. Mark the middle. And mark the middle. Okay? Go back up to the top now and mark the equilibrium position for all of them. So that's the markings you should have right now. Okay, so mark the equilibrium position for all three scenarios and mark the stretched and compressed position as well. Now, in the first case at the top, if it were stretched, that means that this is the stretch x. Agreed?
Yes.
In the formula f equals negative kx, that is x.
Yeah.
In the bottom, this is x. And in parentheses, please put that it is negative in the bottom. In the top, you can write positive, but that might be more clear that it's positive. Now, when an object is, or when a spring is stretched to the right, like in this case, so the first scenario now, so looking up here at this first scenario, what can we say about the force in the spring itself? Not the force that the person is pulling with, because clearly the person is pulling it to the right, but which way is the spring force exerted? Of the, you on first?
Of the applied force, so it's a friction, I guess you can call it.
Yeah, very good. It's a restoring force like friction. Very good. So the force of the spring in this case, if you were to draw a free body diagram, this is the force of the spring in this case.
Tension.
Okay, say again?
Tension.
There's definitely tension, but we're going to call it Fs because it's a spring force, which is a little different from a tension force, but it is a form of tension, a type of tension. In the bottom case, canning, it's compressed to the left, so which way is the spring pushing? Very good. So now the spring force is to the right. Are we all clear as to this, how this works so far?
Oh, yeah.
Okay?
Wouldn't the top one be negative?
The force in the top one would have a negative sign, absolutely. And the force in the bottom one would be a positive value. That is correct. So if you want to write that, you can. Okay, positive, negative. Positive, negative. Now, what we want to think about is, first of all, why this makes sense. Remember our formula?
F equals negative kx.
Okay, take a look. K is always positive. The value, the inherent value of K is always positive. So let's look at the scenarios. First scenario, Fs is negative, which means that we have a negative over here. We have negative K times X, which is positive. So you see there's a negative, negative. What happens to them? Positive. So K remains positive. Look at the bottom scenario. Fs now is positive. It's negative K, but X is now what in this bottom case? In the bottom scenario.
They become both positive.
Yes, very good.
Because when you're both
So since this X down here in the bottom is negative, we have a negative, negative, which still makes the K value positive. It's very important that we see that this formula, Fs is the spring. constant, or spring force. You're making me lose my train of thought because of that. Please, let's go, guys. That's twice in 2 days, this class. The spring force is what we're looking at, not the applied force. Is that clear? The applied force, sure, it's pulling this to the right, but we care about what the spring is pulling with. Okay, what the spring is pulling with. Jeff?
So, with the Fs is the spring force coming back, but I thought the original equation was the applied force coming out. How do you know which one's which?
Okay, the original equation was Fs equals negative Kx.
Hooke's law is just the spring going back, right?
This is Hooke's law right here.
Okay, so then it's always going to be positive, and why do we deal with that negative K?
It's not always going to be positive, though. Look. Oh, no, sorry, Jeff. These are both Hooke's law. Sorry, I meant this equation is Hooke's law.
Yeah.
The equation, F equals negative Kx, is written in both spots.
Yeah.
Those are Hooke's law.
Yeah.
But either way, the K value will turn out to be positive. That's what I was getting at here. Okay?
Exactly, so they'll both be positive.
No matter what, K is positive. Correct.
Okay, so then why is it negative?
It's not negative. The equation has a negative in front of it.
Oh, I see.
Think of it as this, Jeff. Fs equals the opposite of Kx. Don't think about the word negative. Just use the word opposite. Okay, K is not negative. The negative symbol is just in front of the product of Kx. That's all it is. Okay? Now, other stuff to discuss. If I were to pull on this spring and let go, what would happen? So let's say we started at the equilibrium position. I then applied a force to the top to pull this out like this. So I applied a force to the right, extending the spring. And then I let go of it. Assume the floor has no friction at all. There's no friction on the floor. What would happen to the object? Show me with your hand, somebody, or show me with some sort of motion. Okay, and give me the behavior of the mass as a function of time. What would keep happening?
Go back and forth.
Exactly. And what do we call that when something slides? Oscillating. Very good.
So I guess it
Until it dampens enough to get to the equilibrium. Again, if you release the mass, here's what's going to happen. So if you want to go back and take a look at this, at this position up here, the velocity equals 0. Because it stops, right? Think about a spring. If you stretch it and it's oscillating back and forth, when it gets to the end, it's got to stop and then start coming back. And then stop and then start coming back. So at the end points, V is 0. At the middle is when it's going its fastest. So here is where V is a maximum. Okay? It's a tough concept to get your head wrapped around at first. But think logically about what's going on. You're moving this way, you're slowing down till you stop. Then it starts pulling you back, or picking up speed, picking up speed, picking up speed. You hit your natural length, and then it starts compressing the spring, which slows you down, slows you down, slows you down. Then you move back this way, and so forth and so on. So what's happening to your velocity, if I were to draw this as a wave, okay, here's your velocity. Your velocity, so you start, let's say I start by extending the spring, right? I have no velocity now. I have no velocity. Then, and I'm going to write this is time and velocity, V versus T. Okay? No velocity initially. Then my velocity starts increasing. In which direction though is this?
Negative.
Negative. So the velocity starts increasing in the negative direction until I reach a maximum. Then it starts to slow down, which means it's getting closer and closer to no velocity. Then what happens when it starts to push me this way? The velocity starts to speed up in the positive. Then it starts to slow down. That's why this is a wave. It's oscillatory motion. This is a sine or cosine wave. Sorry, Fernando, I didn't mean to steal that. I know in the Algebra 2 class here, you haven't gotten to trig yet, so this is not familiar, which is fine right now. But that's what this is. This is a sine wave that happened to start with a negative, what we call amplitude. Okay, a negative amplitude. So far, so good? We doing all right? Okay, so again, think about this for a second. You start with no velocity. When you're extended, it becomes negative, picking up, maximum velocity in the negative dimension. Then it starts to slow down, until it stops out here. Then it starts to pick up speed until it reaches a max again, but in a positive direction. And then it starts to slow down again until it gets to here. And then what's going to happen?
Continue.
It's going to continue the cycle. This is one cycle. This is one wavelength. Okay? So now let's go into what these mean. So please draw this now. This is called tau in physics. It is a wavelength. Okay? It is the period. The symbol for the actual wavelength itself, if I'm correct, I think is lambda we're going to use here. Okay, this represents the period of time. This represents the actual wavelength itself. Oh, my arm's hurting.
You want me to be your scribe? I'm a little confused.
So, tau is literally, if you looked at a sine wave on a graph, the length from here to here is called tau. Okay?
What?
I'm sorry, it's called lambda. Let me write the words out.
Lambda.
Okay, TAU. For a cosine wave standard, 2 pi is one wavelength, but at higher frequency, it might just be pi, it might be pi over 2, it depends. That's just for a normal wavelength that is not, compressed or extended at all. Alright, so again, tau, this symbol is the period of time it takes for one wave to occur, for one full oscillation. So if I release the spring, the time it takes to go from here, and back is one oscillation. That's tau, the time it takes. The actual wavelength, physically on the graph, is called lambda. Okay? It's called lambda. The amplitude...
I thought it was actually lambda.
The amplitude is the distance from what's called the midline to the maximum. The midline happens to be the x-axis here, okay? The midline is the x-axis, but that is called the amplitude.
There's a lot of stuff.
I know, it's alright.
The distance from midline to what?
From the midline to the maximum velocity. Either way, the top or the bottom. It doesn't matter really, right? Because it's symmetric in a sense.
Right.
Okay? I'm trying to give you guys the gist of things because I'm not going to go into crazy detail with these waves right now. We're going to talk about more wave properties in the next section, but I want you to have an idea of how you can relate this to that oscillatory motion that we've seen today. Okay? Does that make sense?
Yeah, yes.
All right.
Yepers.
Yes.
Yes.
I done did it fun, You done did hurt my feelers. You done did
Mr. Hall, can you let us out 3 minutes early to go down and get changed for B-ball?
Sure. Now, just because you asked nicely.
Yeah.
You were the same shorts as Ashley.
What time does the period end today?
What was that?
10:13.
Okay, so at 10:10, tell me.
5 minutes.
So the last thing I want to talk about today. Pendulum, please. Okay.
Horizontal springs is different from vertical springs.
No.
Horizontal springs feel friction with the ground. Vertical springs feel air resistance as their only form of friction. Okay. So draw yourself a pendulum, please, hung from the ceiling. That's how you draw a ceiling, by the way. Okay. Just put little seriously, even a wall, same thing. So if there was a wall on the other side over here, you would just put a line like that, and that would be the wall right there. Whenever there's a surface in contact. Okay. So there's a pendulum, and what's going to happen is I'm going to release the pendulum. Okay. And show me with your arm what it's going to look like. Yes. Okay? Just going to do this. Okay? Just this. Back and forth. You're going to do this. I don't know what's going on. But we're doing this, right? We're just doing this. Okay? Now, what's going to happen? What's going to happen over a period of time? Realistically, it's going to stop, right? It'll stop. Okay? But we can think of this as the exact same thing as the spring mass. Think about it for a second in your mind. You have no velocity right now. Remember we did this with potential energy and kinetic energy? Right now it's all potential. It's not moving. You release it. It gets to the bottom of the path. There's no more potential. There's all kinetic. So this is where V reaches a maximum. Then it moves back up here, and what's going to happen at here? It stops again. So what's V over here?
0.
0. It is analogous to the spring mass system.
That means it's just similar, right?
It's identical, but its own characteristics.
Okay.
Didn't we learn that in
That's in
art?
colors, yeah.
Oh yeah, we read that in art. Or what? So she thought.
And we're going to call it a simple pendulum. Okay, a simple pendulum. A simple pendulum usually indicates that there is no friction acting on this object. Okay? So you can have no velocity when it reaches its peaks, and when it reaches that bottom point, you're going to have a maximum velocity. This is the same exact thing. Okay, the same exact thing. Now, one thing to notice, and write this on the side, please. Instead of a spring force, instead of a spring force as the restoring force, what is causing the pendulum to fall?
Gravity.
Gravity. Gravity is the restoring force in this case.
What is supposed to say in the bottom left? Negative spring minus mass.
No, sorry, these are just bullets. Spring mass system and a simple pendulum system.
Wait, what was that? So instead of
So
a
gravity is
spring
the
force-
restoring force.
Gravity is now the restoring force for a pendulum, where the spring was the restoring force for a spring mass system.
That makes sense.
Okay? For a spring mass system. Now, please, these are the kind of questions that come up on like that SAT 2 I was talking about. These are the theoretical questions you'll have. And you need to know real life application as well. So, realistically, this is not going to oscillate forever. What the wave will look like is this. And this is kind of cool to see. With no resistance, this is the wave. With no resistance, right? As Jeff said, it goes on forever. Does somebody want to draw what it would look like when there is resistance?
Can I go on the phone?
What would it look like where there is resistance? And what happened to the oscillations over time?
Wait, can I do it?
Good, very good.
Okay.
Okay? So the oscillations minimize. Now,
Should have used your pen.
Now, the really cool part is if you go on to study engineering, you learn at what rate do they minimize, what trend does it follow. So for example, of exponential decay oscillatory motion. It looks like this. It follows exponential decay on both sides. This is an exponential decay graph on the top, and this is exponential decay on the bottom. It bounds it. So you'll see that the motion eventually, and this will become asymptote. Have you learned asymptote yet?
Asymptotes? Well,
Asymptote?
back in the days.
Okay, asymptote is something that gets closer and closer but never reaches.
Isotope.
So it's getting closer and closer here. So it's like getting closer and closer to until it diminishes. What's an example of this damped oscillatory motion you can think of? A good example of damped oscillatory motion.
That's horizontal spring.
A horizontal spring on the floor. Good, because it stops. What else? What else?
Well, I guess if you stop swinging on a swing.
Okay, on a swing itself. Good. So a pendulum, right? That's what it is. When you're on a swing, isn't that just a pendulum?
Oh,
So the minute you stop kicking off the ground, you're going to stop. What else?
Newton's ball. Or Newton's cradle. No, the Newton's cradle. No, I forgot the name of Newton's cradle. The Newton's cradle says slowly. No, I forgot the name. Newton's balls as well.
Fernando. That's correct.
Okay, thank you.
Newton's cradle. Now, one more minute. Newton's cradle, okay, is a very good approximation of something that's almost frictionless because it goes on for a while, but eventually it does stop. What's another example? There's one I always think of that's really the easiest example I always think of. Oh, tired, but that's still pendulum. I'm talking about. Max, guys. If we don't run out of time, we're going to keep talking. I'm going to leave. There's one example of a spring mass system, a spring mass damper system that's the best example. Bouncy ball?
Oh, yo-yo.
Okay,
Oh, I know.
I agree. A bouncy ball over time will eventually stop. Yes, that's good.
What about like at the playground when there's those horses things that had the on spring?
Okay, the horse thing. No, the one that's not the seesaw. She's talking about one that's on a spring and it goes back and forth and it'll slow down.
Yeah.
That's spring, that's off the train when it's like going.
Like a
If a train was to fly into the wall, spring out and stop it.
That's spring like specifically to stop trains, like at the end of the track.
That's what I mean. If a train were to run off the track and fly into the wall. What about your car, guys? Your car is an example. Not the airbag, it's the suspension system. When you hit a bump, when you hit a speed bump, it does this, right? Your car real quick and it diminishes real quick. You would call that a perfectly damped system. It doesn't follow motion like this, but it does something like this. Real quick. It diminishes very quickly. This is a very well damped system. Okay? That makes sense? Okay, think about these examples of real life applications. That's it for 12.1. I'm going to post homework tonight from section 12.1 on Moodle. Make sure you do it. Have a good day. That's equilibrium, okay? Now I take the mass and I pull it all the way to this position. So I'm going to represent the mass with a dot. So I pull the mass all the way outward until it's here. And then I let go. Well, what's going to happen to the mass is this. It's going to slide back toward the front. It's going to compress. Then it's going to come back. Then it's going to go back. And it's going to oscillate forever. Except when there's friction, which in real life there is. So if you think about it, if you take a spring and let it go, it's going to oscillate for a little while until it dampens out and stops. Okay? Similar to that noise. Somebody do that again. Whatever that was. Do that again. One person. Okay. You hear that?
One person.
But does everybody hear that? Relax. You hear that like back and forth? That's an oscillation. That's exactly what that is. It's oscillating back and forth until friction stops it. Okay? I took a video the other day. Let me see if it worked or not. On my phone to show you guys. No. Okay. Sorry. I took a video the other day. Yeah, I had a feeling it wouldn't work for something. I was doing laundry, okay? And I was actually sitting downstairs doing laundry, and my wash machine has been acting up.
You watch your laundry too? Like I watch it.
Oh, watch it. I'm like, do I watch? Okay. So, no, my machine has been acting up. So, for this time being, I was actually watching the machine. I wanted to see what was causing an error. So anyway, I was watching the machine, and it was on like the spin cycle. You know when it gets to like a very high speed? So it's like it's spinning slowly until it gets to a really high frequency. And if you've ever seen a washer, if the floor is not perfectly flat, which mine is not, it's in like a basement, and it's unfinished, so it's like cement. The machine will sometimes rock a little bit, right? It'll rattle. You'll hear like, right? You hear that like change in frequency, okay? Now, listen, gentlemen, come on. I'm saying gentlemen because the ladies are being nice and quiet and polite. The object itself, the machine, it will vibrate, and eventually, if it vibrates at a high enough frequency, the wash machine, you really don't even notice it, you don't hear it, and it'll actually almost minimize the vibration itself, and that's what they're made to do. So when it gets to those high speeds, it stops. But what you'll see is if you look at the machine, and this is going to sound weird, but like, imagine this object here was the washing machine. If you get really close to it and just stare at the side of it, you're going to see it vibrating back and forth like this. And you're going to see this little oscillatory motion. Okay, you're going to see the side of the machine literally just vibrating back and forth, back and forth, back and forth. And that's what this is. Now, on a full scale, we are looking at on a full scale or a real scale, we need to think about the fact that we have friction involved also. There's paper towels over there, that's all I can see. Yeah. There's really friction involved. Stop it, guys. There's really friction involved, and what will happen is this object will eventually come to rest. Okay? Where will it come to rest? At equilibrium. Again, at equilibrium. Okay? Does this make sense so far? Are we clear? Oscillations, go ahead. Well, that was like a picture of the whole scenario. So if you were to take a snapshot when it's extended, a snapshot when it's at equilibrium, and a snapshot when it's compressed. And then it's going to go back and forth and back and forth and back and forth. Let me pull up a video to show you. Yeah, so at equilibrium it's still moving, but it'll pass through equilibrium until it gets to its maximum compression. Then it'll pass through again to get the maximum extension and back and forth and back and forth.
Finest ones.
On the previous page, okay, we already, is it recording? Nice.
I think there's an after this.
We already recorded or indicated the forces, okay, at each location. Now, remember Newton's second law, F equals ma. So, if the object is stretched, the force is pulling back, which means that the acceleration is also in that direction. Again, think about this for a second. When this object, imagine right now that this object is stretched, the force is pulling this way of the spring if it were stretched, which means that the acceleration is also in that direction, because the force and the acceleration go together with Newton's second law. So the acceleration is pulling it back toward its equilibrium position. Now, if it's moving to the right, so imagine I'm moving this way, but my acceleration is this way, what am I doing?
You're slowing down.
I'm slowing down, which is what causes this object to stop. And then do what? Come back. It hits the equilibrium, then it's going and it's hitting the spring. So watch what happens, ready? It hits here, it starts going this way now. The acceleration is still pulling it this way because it's still stretched. So if I'm moving this way and I'm accelerating this way, now I'm speeding up until I reach equilibrium. And at equilibrium, I reach maximum velocity. Maximum velocity at equilibrium. Once I pass through equilibrium, I'm now still moving this way, but the spring is now pushing me this way, which is slowing me down until I stop. Then the spring pushes me this way, and I'm moving this way, so I'm speeding up again. I'm speeding up, I hit equilibrium, I hit my max velocity. And then I start slowing down. Then I start speeding up. Slowing down. Do you follow what's happening here? At equilibrium, you're always going to have maximum velocity. When it's at the end points, you have zero velocity. So if you want to